Welcome to our project about sensorized infrastructure maintenance. We will present our solution for finding leakages and blockages in sewer systems. But first, an introduction. Our task for this project was to design an autonomous sewer inspection system, which can detect damages in a smart way. The sewer system below the gallery at the UT campus is used as the pilot area. The current inspection system involves manual inspection by controlling a CCTV robot which moves through the pipe. The footage is then analyzed by an expert to detect faults. Doing all of this manually costs time and money, and causes a demand for autonomous inspection. As there's a variety of types in sewer defects, we narrowed down our scope to only finding active leakages and blockages in main pipelines. Our research can be divided in three types. The first one is contextual research. We interviewed an employee of the UT facility management in order to get information on the current inspection system and background information for the pilot area. The second one is literature research. This took the most time and included a lot of research on existing inspection methods. Their limitations and advantages were very important to coming to the final concept. The last one is stakeholder analysis, which will be discussed later on.
The method which was used as the foundation of the design project was system engineering. This method is very structured and therefore guided us through the design phases step by step. Its main focus is not to think of specific solutions right away, but instead focus on a lot of different ways the main goal can be achieved. The used V model has a lot of phases, as you can see in the bottom left, but only 2 iterations were done since time was an important factor. As the bottom right figure suggests, there are 3 core elements and 4 feedback elements involved per iteration. These loops also mean that the iterations are continuous. For example, when a preliminary requirement list has been created, the functional analysis and allocation will be done. However, when a function cannot be linked to a requirement, the requirement list has to be updated. After verifying whether all the objects are linked to the requirements via the functions and validating with the tutor if all changes are sufficient, the next iteration can begin. The first step of system engineering is to conduct a stakeholder analysis in order to get an understanding of who is being influenced by the project and additionally to come up with requirements which the final system has to fulfill. The requirements will be ranked using the Moscow method, which separates the requirements based on importance, so must have, should have, could have, and would or wouldn't have. The slide shows a few keywords which are linked to these requirements. Since requirements can be met with different functions and objects, 3 concepts were developed, and Menno will mention them in the following section.
A broad range of concepts were formed using the functional analysis and existing inspection and sensing research. The first alternative was a tethered ball with a docking station. The ball rolls with the wastewater flow and uses acoustic sensing to listen for leakages. The second alternative was a CCTV robot, which autonomously navigates the sewer system and uses deep learning to identify leakages and blockages. The third alternative was static ultrasonic sonar sensors placed inside the pipe at certain intervals. They send real-time data to the facility management. The performance of each alternative concept is evaluated, and one is chosen using multi-criteria analysis. The criteria are derived from requirements and weighted using SAT-A scale of comparison. The criteria is shown in the right image. The ball concept proved to be the best due to strong performances in cost effectiveness, convenience, and sustainability criteria. The ball concept is therefore taken to the next system engineering phase where the concept is developed to a higher level of detail. During the second systems engineering iteration, changes were made to our design as more research was done. Regarding locomotion, the ball remained non-motorized. However, we did look into motorizing the ball to pull the cable further and keep it in tension. However, this came with further costs and noise disturbance to the acoustic sensors. Regarding autonomy, we went from a docking station to manually inserting and extracting the ball. This was because we could not justify the cost of permanent docking stations when inspections took place only once a year maximum. Regarding localization, we went from using the cable length to determine the location of the ball to manhole magnets and dead reckoning. This was because of stricter ball location accuracy requirements and complications with the tethered system.
Now I will explain our final concept. You can divide our system in 5 stages. We will start with the deployment stage. A human operator goes to the extraction point to install a fishing net, which eventually catches the ball. Then, at the insertion point, the ball will be equipped with a foam shell to reduce noise caused by the ball's movement. Finally, the ball will be inserted with a claw. The ball consists of several sensors: the acoustic sensors, accelerometer, gyroscope and magnetometer. Each of them serve a purpose. The acoustic sensors observe the distinguishable emitted sound from active leakages in the pipe. The accelerometer, gyroscope and magnetometer are used to approximate the ball's location in the pipe. This is later needed to determine where exactly the problem is in the pipe, and will be explained later. In addition, the accelerometer is also used for blockage detection. The ball doesn't have some kind of motor for locomotion, because rolling with the water's flow is already sufficient. Note that I said rolling instead of floating, because the ball won't detect leakages when it's floating. Facility management provides us a map of the UT sewer system, as shown at the right bottom. The image here is narrowed down to our gallery pilot area. It's marked green. The red dots at every change of direction are manholes. After the ball has been catched, the foam shell should be removed to access the aluminium core. Next, the core should be opened to access the ball's data and to charge the ball's battery. The extracted data will be imported into a computer program to perform computations. Data analysis by humans is very time-consuming and requires experienced analysts. That's why a leakage detecting AI would be very beneficial. When a system would be initially deployed, analysis is done manually by experts. But over time, more and more acoustic data will be generated. This largening dataset can be used to train the AI for leakage detection. For blockage detection, the accelerometer is used. Abrupt changes in acceleration can indicate blockages. For example, when the acceleration suddenly becomes 0, then this could mean that the ball bumped into something. Using acoustics involves one problem: noise. This should be reduced by pre-processing the data with software filters. Now the question remains where exactly these leakages and blockages are in the pipe. For this, we use a process called dead reckoning. An accelerometer and gyroscope estimate the current position based on the previously measured values. However, over time a huge error will occur due to approximation. Luckily, you can correct this error if you have external reference points. We know the locations of all manholes, so they can act as the reference points we need. But how does the ball know when it passes a manhole? Well, magnets should be placed at every manhole, which can be detected by the ball's magnetometer. So when should you inspect next? This really depends on the pipe's state. Facility management said that when the pipe is in good shape, you could inspect it again in 5 to 6 years. But when it's bad, you could say once a year. This is a matter of interpretation. Sometimes found leakages and blockages aren't worth the cost to fix, because they are too small. This is the case when inspection should be done once a year to keep an eye on the problem, but only fix it if it becomes worse.
Since only the first 2 iterations of the V model have been covered, there are still some aspects of the final design which could be improved or require further research. Additionally, as mentioned in the scope of the project, the system is designed to be optimal for the pilot area. The impact of noise influencing the acoustic data should not be underestimated. They could partly be achieved by improving the data analysis by creating a larger data set for the AI. If the ball should inspect other sewer systems, the localization of the ball could turn out to be a problem for larger networks, because all the manholes in the system should be equipped with the magnets. A crucial aspect that also needs further research is the dead reckoning method. There needs to be assurance that the frequency of the reference points, in this case the manholes, is enough for the location to be precise to some extent.
To conclude, our design solution excels compared to the currently employed method of manual CCTV crawlers, as it has autonomous locomotion, inspection and data analysis. It also has lower labour time and costs because an unskilled worker can operate the ball. It can also operate whilst the sewer is in use. However, this solution doesn't come without its limitations. The ball is limited to our scope of leakage and blockage detection. Acoustic sensors are still prone to noise disturbance. Magnets are needed to be placed at each manhole, and faulty acoustic sensors can only be identified during the data analysis stage. Thank you everyone for your attention, and we look forward to your questions.